guys, it's me, Julian. Today's video is on density and unit analysis.
So hello everyone, try to recall density. That is how much mass is packed into any particular certain unit of volume. Typically we use grams and cubic centimeters. So for instance, liquid water has a density of what we say 1 gram per cubic centimeter at around room temperature. Common symbols are lowercase d, or maybe this thing that looks like a P, it's the Greek letter rho. These are density. So density expresses an equivalence and not an equality. It's silly to say that 1 gram is equal to 1 cubic centimeter, but it's true that 1 gram of liquid water is equivalent to 1 cubic centimeter of liquid water at some temperature. So let's put this idea of equivalence to work and introduce this new notion we're going to call unit analysis. Sometimes this is known as the factor label method. You'll see it written that way in some books. In our first sample problem today, let's look at this ammonium magnesium chromate. It has a given density, and we're supposed to find the mass of some volume of it. You could take the approach that density is mass over volume and solve an algebraic equation and work out a value. Or let's see if we can put a unit analysis to work. Start with 8.34 cubic centimeters of the material. That's something that we know. Now notice we want to cancel the cubic centimeters, so put them on the bottom. Grams we want, they're on top. Check the units cancel. They do. We want it with this large number of digits here. Please check. You have 3 significant figures in our problem, and so we just write here 16.0 grams. Notice you didn't have to remember whether to multiply or divide by the density, you just follow the units. Also, it's worthwhile because you can check before calculating. You have some confidence, you know you've got the right answer before you pick up your calculator. Here's the cesium sulfate. Let's try unit analysis on this problem. We're given the mass of some of this stuff, we want to find its volume. So let's start with something concrete that we know, that we have. And that is this 776 grams of the substance. We don't get of grams, so put them on the bottom there. 2.89 grams every 1 cubic centimeter. That's the density, this time it's upside down. Notice that we didn't have to think about that though. We just placed the units first, and then the numbers, and just let the order take care of itself. Check here that the grams do cancel. We went up with cubic centimeters. That is volume, which is correct. And you get some number here of cubic centimeters. Notice this problem has got 3 significant figures, so we'll round to the third spot and call this 269 cubic centimeters. Are you ready for more? Let's try this one. Let's convert 120 kilometer per hour to meter per second. We'll just convert the kilometers to meters like this. There's 1,000 meters for every kilometer. Then we'll convert here the seconds to hours. There's 3,600 seconds for every hour. Notice those all cancel. And we wind up with meters per second. This is 33.33, and if you look closely, there's 2 significant figures in this problem. Trailing zeros don't count. We wind up with 33 meter per second. So let's keep on here and see how many minutes you have to flow an electrical current of 55 coulomb per second to get 420 coulombs. Remember to start with a concrete value that you know. In our case is that 420 coulombs. Every 1 coulomb per second, there's 55 coulombs every 1 second here. 60 seconds in a minute. Cancel, cancel, cancel. Wind up with minutes. That's what the question was looking for. And here's our value. Notice the problem has got just 2 significant figures, so we'll make that 0.13 minutes. Again, units first, numbers afterwards. Here's a nice introduction to the mole concept, trying to count the number of atoms in a 10-gram sample of gallium. Let's start with our 10 grams of gallium and then use the information that we know. That for a certain number of grams there are so many atoms. This is true, mind you, for gallium only. And if you put in these values here as given in the problem, you see we wind up with atoms of gallium. 8.63 by 10 to the 22 of them. It's quite a lot of atoms of gallium actually. There's 3 significant digits in our problem, and there it is. If you're doing so far so good, let's try one with several steps. Here we have to convert 105 feet per second into kilometer per hour. So we'll convert the feet into inches, the inches into millimeters, as given in the problem. Then let's do the millimeters into meters, and because we're taking a long way around, we'll do the meters into kilometers, and finally we'll make the seconds into hours. Cancel, cancel, cancel all the units, and you wind up with kilometer per hour. Turns out to be 115 point some kilometers per hour. Notice just 3 significant figures in our problem. Make that 115 kilometer per hour. So let's recap a unit analysis then and see if we can make some sense out of it. Here we go. First of all, keep the numbers and the units and the species together. Second, mind the units first and let the numbers follow. Check also the units before you calculate, be sure they're right. And finally, give the results with the correct number of significant figures and units. And that's about it. We'll practice this quite a lot more in our course. So, thanks a lot, and see you soon. Have a look at the next 2 videos in the playlist for more, and stay tuned for our next lesson in Chemistry 11, Lesson 6, Calculating with Significant Figures.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!